You're traveling through space, long way to go. But suddenly, your spaceship starts to distort. You rush towards the window, stunned to find you're facing those two bent strips of light. The last thing you expected to see, surely, the first in your fears. Unfortunately, it's now too late. As you fear, accept your fate. You have fallen into a black hole. But how did we get there? To have a clear understanding of this, we must go through some history first. John Michell, an English clergyman and astronomer, proposed the idea of black holes in 1783. He was inspired by Newton's law of universal gravitation and the concept of escape velocity. Michell realized that a star with a density so high that its escape velocity exceeded the speed of light would appear dark, as not even light could escape its grasp. However, the modern understanding of black holes began to take shape in the 20th century with the work of Albert Einstein. His theory of general relativity from 1915 predicted the existence of black holes as singularities with infinite density and zero volume. We will discuss this further in the video later on. General relativity is a fundamental theory of gravitation. It revolutionizes our understanding of space, time, and gravity. The theory postulates that gravity is not a force, but the curvature of spacetime caused by the presence of mass and energy. According to general relativity, the curvature of spacetime around a massive object, such as the Earth, causes objects to fall towards its center, which we experience as gravity. The theory is based on the principle of general covariance, which states that the laws of physics are the same for all observers in uniform motion. In the 1950s and 1960s, scientists like David Finkelstein, Martin Schwarzschild, Roger Penrose further developed the concept of black holes. They explored the properties of these singularities, including their event horizons, which mark the boundary through which nothing can escape. The first ever black hole was detected in 1971 by a team led by Riccardo Giacconi. It's named Cygnus X1. This binary system consists of a massive O-type star and a compact object that was later confirmed to be a black hole. In case you don't know, O-type stars are extremely massive, luminous, and hot stars with surface temperatures over 30,000 Kelvin, intense radiation, and strong winds, often associated with black holes and neutron stars. Now let's discuss the three main parts of a black hole structure: the event horizon, singularity, and the accretion disk. Starting off with the event horizon, it is the point of no return around a black hole, marking the boundary beyond which anything that enters cannot escape. Once crossed, the gravitational pull is so strong that even light is trapped, making it invisible to the outside universe. The event horizon is not a physical boundary but a mathematical concept, marking the point where the escape velocity exceeds the speed of light. It's the point of no return, where the black hole's gravity takes control. Any matter or radiation that crosses the event horizon is inevitably pulled towards the singularity, where it is consumed and added to the black hole's mass. Now you might ask that if black holes trap their own light, how do we know what they look like? This is where the second part of the structure comes in, the accretion disk. It is a rotating disk of gas and dust that surrounds a black hole or other massive object. As material falls toward the center, it becomes hotter and denser, releasing a tremendous amount of energy in the form of X-rays and other forms of radiation. We can detect these radiations with specially designed telescopes, but more on that later. The disk is characterized by its high temperatures, intense magnetic fields, and strong gravitational forces. Accretion disks are a key component in the growth and evolution of black holes, and they play a crucial role in the formation of stars and planets. They are also responsible for the observed luminosity of quasars and active galactic nuclei. Lastly, we have singularity. The singularity is the very center of a black hole, where the density and curvature of spacetime are infinite. It's a point of zero volume and infinite density, where the laws of physics as we know them break down. The singularity is thought to be a point of infinite gravity. It's the point of ultimate collapse, where the matter and energy of a star are compressed into an infinitesimally small point. But according to fundamental physics, infinites cannot exist, so singularity is just another theory. The singularity is a mathematical concept, and its nature is still a topic of much debate and research in the fields of astrophysics and cosmology. The singularity is a one-dimensional point, and its properties are still not well understood, making it one of the most fascinating and mysterious objects in the universe. When a massive star runs out of fuel, its core collapses under gravity, causing a supernova explosion. If the star is massive enough, the core collapses into a singularity, creating a black hole. Alternatively, the merger of two neutron stars can also form a black hole. The immense gravity of these events warps spacetime, creating a boundary called the event horizon. Inside the black hole, this process creates a region of spacetime with infinite density and zero volume. There are a few more theoretical ways through which black holes are formed which are yet to be proven. Stellar black holes are incredibly dense regions of spacetime formed from the collapse of massive stars. These black holes can have masses millions or even billions of times that of our Sun, making them some of the most extreme objects in the universe. Despite their intense gravity, stellar black holes play a crucial role in the formation and evolution of galaxies. Intermediate mass black holes have masses between 100 and 100,000 times that of the Sun, bridging the gap between stellar and supermassive black holes. Their formation is still a topic of research, but possible scenarios include the merger of stellar black holes or the collapse of massive stars. These black holes could be found in the centers of small galaxies, globular clusters, or even the Milky Way's bulge. Their existence could help explain certain astronomical phenomena, such as the observed star formation rates in galaxies. Supermassive black holes reside at the centers of galaxies, with masses between 100,000 to 10 billion solar masses. These behemoths are thought to have formed from the merger of smaller black holes. Supermassive black holes play a crucial role in shaping galaxy evolution, regulating star formation, and influencing the surrounding environment through their immense gravity and energy output. They are among the most extreme and fascinating objects in the universe, with the one at the Milky Way center being a prime example. It's called the Sagittarius A. Micro-black holes are hypothetical, tiny black holes with masses much smaller than stellar black holes, potentially created in high-energy particle collisions or by advanced civilizations. They would have incredibly small event horizons and evaporate quickly through Hawking radiation, making them challenging to detect and study, but fascinating theoretical concepts. This part of the video is probably the most fascinating and interesting. Black holes have a profound impact on our understanding of time. Their incredibly strong gravity warps the fabric of spacetime, causing time to behave in strange and counterintuitive ways. Time dilation occurs near the event horizon, causing time to slow down for objects approaching the black hole. This effect becomes more pronounced as the object gets closer, eventually appearing to stand still for an outside observer. For example, if a clock were to fall into a black hole, it would appear to slow down and eventually freeze in time, from the perspective of an observer watching from a safe distance. In addition, the curvature of spacetime around a black hole creates closed time-like curves, which could potentially allow for time travel. However, the technical difficulties and potential paradoxes associated with this idea make it more of a theoretical curiosity than a practical possibility. Black holes play a crucial role in the universe, driving galaxy evolution, regulating star formation, and shaping cosmic structures. Supermassive black holes at galaxy centers govern gas dynamics, fuel quasars and active galactic nuclei, or AGN, and emit intense radiation. Stellar mass black holes, formed from star collapses, influence binary and multiple star systems, star cluster dynamics, and cosmic feedback. The three common ways by which a black hole can be detected are X-ray emissions, gravitational waves, and the behavior of stars close to black holes. Black holes can be detected by the X-rays they emit. Telescopes like NASA's Chandra X-ray Observatory and NUSTAR can detect these X-rays, revealing the presence of a black hole. The X-rays are produced when hot gas swirls around the black hole, creating an accretion disk. By analyzing the X-ray spectrum and intensity, scientists can infer the black hole's mass, spin, and accretion rate. The detection of gravitational waves by Laser Interferometer Gravitational Wave Observatory and Virgo collaboration in 2015 confirmed the existence of black holes. Gravitational waves are ripples in spacetime produced by violent cosmic events, such as the merger of two black holes or neutron stars. As these waves pass through Earth, they cause tiny distortions in space and time, which can be detected by sensitive instruments. The detection of gravitational waves from black hole mergers reveals the black hole's mass, spin, and orientation. The behavior of stars close to black holes can reveal the presence of these cosmic monsters. Stars that venture too close to a black hole are stretched and compressed by its intense gravity, causing them to brighten and dim in a characteristic pattern. By observing the motion and brightness of stars near a suspected black hole, astronomers can infer its presence. For example, stars may be seen moving at high speeds or following elliptical orbits, indicating they are bound to a massive, unseen object. Additionally, stars may disappear or reappear as they pass behind the black hole, a phenomenon known as gravitational lensing. By monitoring the behavior of stars, scientists can identify black holes and study their properties. Black holes are fascinating and mysterious objects that continue to intrigue scientists and the public alike. Their incredible density and gravity warp spacetime. Through observations of X-rays, gravitational waves, and star motions, we've confirmed their existence and studied their properties. Their study has led to a deeper understanding of the universe, and ongoing research promises to reveal even more secrets about these cosmic enigmas. We hope you enjoyed this little documentary and learned something new from it. Before you leave, hit the subscribe button and stay tuned for our upcoming videos.